You know what's going to happen is 6 months from now, I'm not going to remember any of this, and I'm going to get on Blackboard and I'm going to ask why does my profile picture look like Squidward? And then I'm going to remember all this chat before class, and it's gonna get the memory banks rolling. All right, let's get started. I had a couple of housekeeping items I wanted to run through before we get into our topic today. Let's take care of the housekeeping first. So as of right now, all of the homework is graded that's outstanding, obviously, other than the one that was due right now. All the homework's graded, all the solutions are posted, and the YouTube playlist should be up to date as of today. I wanted to mention a couple other things. I've been doing this ever since we started doing the online lecture, and I'm not sure if I actually explicitly mentioned it. So if you go to Blackboard and you go to the Grade Center, I think it's in the Grade Center. You have to forgive me. As a professor, we have a little bit of a different interface than the students do, but I believe if you go into the Grade Center, and I don't know, let's say it's like homework 6.2 or something. If you click homework 6.2, you should see not only your grade for that homework, but you should see the feedback that I left. And I wanted to make a point of making sure that if I gave you, let's say you have a homework assignment, it was worth 10 points and you got like 9 points. I wanted you to know why you got those points off. So I made sure to leave everybody feedback as to like what was done wrong, because I didn't want you to turn in a homework and just, oh, I got an 80 and I don't know why I got it. So everybody should be able to get that feedback. Also, if you have not yet, okay, when you click My Grades, once you're in the Blackboard page, you'll see a chat bubble. Yeah, okay, so you should see all of the feedback as to like what deductions were made and why they were made. And so I wanted to make sure everybody was aware of that. And you ought to check those out, because a lot of times we'll have a homework assignment and we'll have homework, I don't know, 8.1, and then homework 8.2 sort of relies on that. So I want you to know like what you did wrong so you wouldn't do it again on the next homework. I also want to make sure that everybody's aware about Microsoft Teams. I mean, I know we had that post in the beginning of the semester. Every time that I finish grading a homework, I make a post on Teams so that everybody can see what the class average was on the homework and what were some general mistakes that everybody made, because when you have the like an assignment like this, you'll have some common conceptual errors, and so I wanted everybody to be aware of that. So I would check the Teams chat for regular posts. If you haven't already put Teams either on your desktop or on your phone, I would do that, because I'll post and let you all know when the when the YouTube videos are up to date. Things about just clarifications on homeworks and things like that. And I figure that might make things a little easier for you, so that your inbox, your email inbox, isn't just slammed with a bunch of stuff. Because I don't know if your inbox is anything like mine, but ever since we've gone to distance learning, I mean, the university, students, faculty, I mean, we're just getting slammed with emails with all sorts of different things. And I just figure if you're interested in just feedback on concrete design, just go to Teams, and if you go to that channel, it's nothing but concrete design stuff there. And so it's a little easier to navigate through stuff. I mean, don't get me wrong, you can still email me if you want. Please feel free to do so. But I figure it's just a way of isolating some of that email chatter and just putting everything there, so I'm not sending an email every time my homework's graded and whatnot. I wanted to also mention, I'm still going to go ahead and do the bonus points for the course evals. I'll be honest, I am interested in everybody's feedback, not just about concrete design as a whole and what we were doing prior to the distance learning, but also the steps that have taken since we've gone to distance learning. I mean, obviously the homework schedule is a bit different. It's more rapid delivery. You have an assignment due every day, and I just want to get your feedback on that. I mean, we're all learning new tricks now that we've sort of been forced to do everything at a distance, and so I kind of want to get your feedback on what worked and what didn't, because I mean, we're all sort of learning how to get through this, myself included, and so I really do value the feedback, but not just on that, just on concrete design as a whole, and any suggestions you would have about the class. Um, any quick questions just about logistics or anything before we get into the topic today? All right. Today's going to be a little different for our topic. If you go to our class schedule and the COVID schedule, I had that we were going to cover development length of hooks today. And I got to thinking, and I kind of decided not to do that, and I'll tell you why. I think that most people, like I was skimming through the homeworks as they were coming in, and I think most people found that the development length calculation was really easy. And it is. I mean, it's just a plug and chug equation. The development length of hooks is no different. It's just a different equation. A couple of the factors are different, but it's no more plug or chug. It's no more complicated than the development length of straight bars. It's just a different equation and different factors. And I'm about wanting to make sure that you all get the most bang for your buck and that you learn some stuff about concrete design. I have every faith in your ability to open up a book and read an equation and plug and chug. And really, that's all development length is. And I think it wouldn't really be a valuable use of our time to just do another development length equation and calculation. I want to make sure that you all understand concrete design. And so when I was grading the deflection homeworks, I noticed like a conceptual error that popped up on a lot of people's homework assignments when it came to deflections. And so what I decided to do was sort of go back to that, and I want to talk about deflections again and show you a conceptual error that a lot of people made, and I want to make sure that everybody's clear on it. And then what we're going to do today for our exercise and for our homework is actually just some structural analysis. We're going to go back and do some basic deflection calculations and some basic problems, because when you for two reasons. One, when you take your final, I mean, we're going to have deflections on the final. We're going to have this stuff on the final. And what I'm finding is that setting aside just some like calculator issues, like plug and chug issues, everybody seems to get the concrete design. Like the concrete design's the easy part. But barring this conceptual issue, it seems like just like finding which formula to use for structural analysis, I don't want that to be a barrier in the concrete design. I want the structural analysis to be simple. So, and I'm about your success. So it's like, let's talk about that first. So let me play this slideshow. Let me hit play on this. Okay. I want to go through deflections, and I want to talk about the homework assignment that we just did, namely homework assignment 7.2 and 7.3. So let's get everybody back into the speed of what it is we were talking about. So we had a homework problem that looked like this. Homework 7.2 was immediate deflections. Homework 7.3 was long-term deflections. They both revolved around the same problem. We had a gross moment of inertia of 10,000 inches to the fourth. We had a cracked moment of inertia of 5,000 inches to the fourth. We had a cracking moment of 40-foot kips, a Young's modulus of 4,000 KSI. The problem stated that there was no compression steel, so we had a rho prime value of 0. And the loads shown include the beam self-weight. So this, let me see here. This 0.75 kips per foot, we're going to say that includes the self-weight, so we don't need to go through and figure that out. Now, another thing, we need to assume that 40% of the load is sustained, and that's sustained for a period of 15 months. And so that's going to affect time-dependent calculations. But that really wasn't the conceptual issue. I really want to go through just the staged construction stuff and talk about the deflection calculations, because there's a big thing I want to make sure everybody's clear on. So let's start off with some base formulas and some base values. Okay, the first thing I want to focus on are these right here. Okay, so we have two load events on this beam. We have a distributed load and a point load, or a concentrated load. The distributed load is along the entire span, and the point load is at midspan. Now, these two formulas here on the left are the moment and deflection expressions if you have a simply supported beam and a uniformly distributed load. So when you have a simply supported beam and a uniformly distributed load, the moment is WL squared over 8, and the deflection's 5WL to the 4th over 384 EI. We're not going to use that right now because down here we're just doing moment. For the concentrated moment, the moment equation is PL over 4, and the deflection is PL cubed over 48 EI. And to be clear, I'm perfectly content with showing you where these equations come from. I mean, we can do the derivation. Like the moment ones are very easy to come up with. They're not really magical. It's just drafting the moment diagram and doing it like we did in structural analysis, just keeping everything in symbols and letters instead of numbers. So our moment expression is PL over 4, and our deflection is PL cubed over 48 EI. So let's take a look at the moment calculations. So for the moment for the dead load, that's the distributed load, so that's WL squared over 8, and so that came out to like 68.3 foot kips, so 0.75 times 27 squared over 8. One thing I'll mention, please make sure that when you're doing this stuff that I think it's a really good practice to plug the values into your calculator, get an answer, and then do it again. Plug the values into your calculator again and do it again. Because you want to make sure that you're not, running down a rabbit hole because you hit buttons in the calculator wrong. It doesn't take a lot of time to do it, and I promise you, you will save yourself a lot of headache in the future, and honestly, your grades, like your exam averages and homework averages, will go up, and it's like free points. So I would definitely do that. The dead load moment came out to about 68.34 for the live load. The point load is 24. The length is 27. So 24 times 27 over 4 is 162. Now, for the sustained live load, the previous slide said that 40% was sustained. So what that means is the moment, the sustained live load moment is 40% of the live load moment, but the same thing is true of the point load itself. So the sustained live load is 40, or the sustained, or the live load is 24 kips. The sustained live load is 40% of that, or 9.6. And the live load moment is 162. 40% of that is 64.8. So here are our dead load and live load and sustained load. These are over here on the left. These are the moment values, and over here on the right, these are just the loads themselves. Does anybody have any questions about this before I move on to the next slide? I want to make sure this is clear. It might seem like for some of you, it might, I hope I'm not boring you, but I really want to make sure this stuff is clear because there's a conceptual error coming up that, again, a lot of people made. Whoa. My screen went off. Can everybody still hear me? Because it just sort of went blank. Okay. Yeah, I don't know what happened, but I was looking at the slides and it just went away. So, okay. All right. And can you see the slides? Okay. All right. Let's keep on tracking. Okay. So let's start off with the deflection of stage 1, which is the dead load, okay? And most people didn't have a problem with this, okay? So, but I want to walk through, one step at a time. In order to determine the dead load deflection, you have to do 3 things, okay? The first thing that you have to do is you have to compute the applied moment. Now, this is stage 1, so the only thing that's on the beam is the dead load, okay? So the applied moment is the applied moment from the dead load, and so that's the 68.3 foot kips. Okay, that's step 1. Step 2 is once you determine your MA value, you then need to determine an effective moment of inertia. Now, I'll go ahead and tell you that probably about a third of you were still having problems with just taking this equation and chugging it out, and I don't think that's anything to be embarrassed about. This is a weird equation. Again, this is a perfect example of do the calcs, like chug it in your calculator, and then do it again. Just repeat it. Do it from scratch, and make sure that you're getting the right answer. Okay. So again, our cracked moment of inertia, that's 5,000. So that's here and here. That's 5,000. The gross moment of inertia, that's 10,000. Our cracked moment, or our cracking moment, is 40, and then MA, this is our 68.34. So whenever we repeat the IE calc over and over again, nothing changes except for the MA value. Everything else stays the same. So MA is the same. Okay. Now, from there, the next thing that you do is you now compute your deflections. Okay. So we've got our stage 1 deflection, which is 5WL to the 4th over 384 EI. So let's just track those values. W is the 0.75 kips per foot. Our 27, a length is 27. A couple of you had put 24 there, and because that was the load, and that's an easy mistake. There's nothing wrong with that. I mean, it was wrong, but that's an easy mistake to make. 27 to the 4th, 384. E is 4,000. I comes from up here. And then don't forget your conversion factor. Your conversion factor is 1728. And then when you chug that out, you get a deflection of 0.414 inches. And most people got that. Most people got that right. Okay. Now what I want you to do for the next couple slides is I want you to keep 0.414 in the back of your head. I really want you to memorize that number because it relates to an error that a lot of people made. But before I move on, is anybody have any questions about this? I'm going to give everybody a sec. Okay. All right. So let's look at stage 2. Okay. Now, whenever you're doing these deflections, what you ought to do is treat each stage like it's its own deflection problem. Okay. And so we're going to do everything we just did again. Okay. We're going to carry it through to the very end, and then we'll look at the error. Okay, so the applied moment. Start off with the applied moment. What's the applied moment? Well, this is the stage that's experiencing dead plus live. So the applied moment is the applied moment from the dead load plus the applied moment from the live load, and so that comes out to about 230.3. Okay, so once you've got your applied moment, you recompute your effective moment of inertia, and you get 5033.73 inches to the 4th. And so again, it's the exact same numbers from the previous slide. The only thing that's different is instead of an MA of 68.3, it's an MA of 230.3. Now, one check to make sure that you're doing the calculations right. If you go from stage 1 to stage 2, the moment increased. So if the moment increases, the MA, if the MA gets larger, your IE value should get smaller. Okay, look at IE. We got 5033.73. From the last step, it was like 5144. That's because with more moment on the beam, more of the beam is cracked. Okay, and with more of the beam cracking, it's going to get weaker, and so the moment of inertia goes down. Okay, now once you got your moment of inertia, you can do the deflection calculation. And so here's the formula. Okay, so we have 5WL to the 4th over 384 EI plus PL cubed over 48 EI. Okay, and so that equals 5WL to the 4th over 384 EI, so 0.75 kips per foot, 27-foot span, our conversion factor, 384, 4,000, moment of inertia from up here, plus PL cubed over 48 EI. P is 24 kips, L is 27, conversion factor, 48, 4,000, 5033.73. Now, I'm not carrying that calculation out just now. All I'm asking before I move on is everybody okay with how I set this up? I'll give everybody a sec to see if they have any questions. All right. Now, here's the error. Here's what a lot of people did. So let's look. I want everybody to pay attention to this part right here. Okay. So all this is what I got from the last slide. That's just this formula right here, copy and pasted. And so here's what a lot of you did. You said, well, the dead load deflection is the deflection from the dead load plus the deflection to the live load. And you think, well, I already did the dead load deflection, right? I got a dead load deflection of 0.414 from the last step. So I don't want to redo this calculation. I'll just replace this with 0.414 because I already did that calc. Okay. Now, we got a lot of social distancing going on, so you can't quite get somebody else to do this. You have to do this to yourself. Do this for yourself. But whenever you feel yourself wanting to do this, don't do that. That is wrong. Okay? That substitution is not correct. You can't use the dead load deflection from stage 1 as a shortcut for stage 2. You can't say, well, I don't really feel like chugging all that out, so I'm going to just use my old deflection value and plug and chug. That doesn't work. Okay? The reason why is because of your moments of inertia, your IE values. Okay? What I did on the next slide is I copy and pasted the stuff from the last 2 slides. So if you look here, okay, this is the formula for dead load deflection from stage 1. This is the formula for dead load deflection from stage 2. They're not the same, okay? They're not the same because of the moments of inertia. They've changed. This is the moment of inertia from stage 1. This is the moment of inertia from stage 2. So that 0.414 does not stay 0.414 in stage 2. In stage 2, the beam is experiencing more load. So more of the beam has cracked. So the dead load effect by itself is worse in stage 2 than it is in stage 1 because of that additional load. That's the whole point of staged construction. You can't use the deflection value from the previous stage in order to compute the deflection values in this stage. If we could do that, we wouldn't have to go through computing dead load deflection and then dead plus live and then taking the difference. Because if you were going to do that, you could just compute the live load deflection by itself. And you can't do that because under live load, the beam is experiencing the dead load as well. So you have to account for all of it. Okay, that conceptual error, like a lot of people did that. Okay, and so I wanted to make sure that that was clear. And again, the mathematical reason why you can't use the 0.414 from step 1 is because the 0.414 uses this moment of inertia, but in step 2, the moment of inertia changes. Okay, I'm going to give everybody a sec to see if that makes sense and to see if anybody has any questions. Yeah, again, I think talking about this is way more important than just a plug and chug equation for hooks. I mean, that stuff is really easy. This is worth our time. I'll give everybody a little second, then I want to move forward on a deflection problem. Is everybody okay on this? Because the reason I'm covering this, we're going to have this on the exam. Like this type of problem will probably be on the test, and so I don't want to just. It's probably one of the most challenging conceptual situations that we're going to deal with for the rest of the semester. So I thought it was worth the time to discuss. I don't want to harp on this forever, so let's go to what I really want to cover for the rest of class today. Instead of covering the other development length equation, because again, it's just plug and chug, it's not difficult, I want to make sure that everybody is completely comfortable with the structural analysis. I mean, this course, the prerequisite for it is structural analysis. So of course, I have an understanding that everybody can do the required structural analysis, but at the same time, we have been using a lot of shortcut equations like WL squared over 8 and things like to perform the structural analysis. But I want to make sure that everybody is crystal clear on what formulas to use and why you should use them. And so this exercise really doesn't have much to do with concrete design per se, but it's meant to familiarize yourself and make sure that everybody is super comfortable with the analysis aids that we've been using, because we're going to see these analysis aids in the future, and I want to make sure that we're all comfortable with using them. So what I did is I pulled a case that we haven't used in any of the examples in class, and really in either class, in steel or concrete. And I just want to look at this example and make sure that we're all clear with determining shear, moment, and deflection for a typical loading scenario. Now, this is just a basic structural analysis exercise. There's no load factors present, none of that stuff. I just want to do the analysis. I have a beam. Now, one of the other things about this beam, this is indeterminate. This is actually an indeterminate problem. That's not going to matter for us doing the basic analysis because the design aids that we can use will handle this. But I just want to make everybody aware that this is indeterminate. Now, I want to know what the maximum shear is on this beam. I want to know what the maximum moment is on this beam. And I want to know what the maximum deflection is on this beam. And I also want to know where they occur. I don't want us to just find a value and say, here it is. I want to know where these values are. So let's look at this beam. And first thing I want everybody to do is this. I want everybody to go to the following. Let me pull it up. And I'm going to ask chat for help on this. So everybody here should be familiar with this. We've used this very, very prevalently in the class. This is our design aid that we've been using to, or analysis aid, I should say, to analyze beams. This is figure 1. Figure 1 is our simply supported beam, uniformly distributed load. Everybody should be familiar, you know, with like WL squared over 8. That's where we got that. That's where we got 5WL to the 4th over 384 EI for deflection, so on and so forth. I want to use this aid to do this problem, okay? So the first thing I'm going to ask chat to do, and I'm going to give everybody a second, I want chat to go into this and tell me which figure, this is figure 1, right? Tell me which figure is applicable for this problem. So again, hopefully everybody's going to that supplement and leafing through it and finding which one is applicable for the problem. There we go. Figure 29. That's exactly right. Let me go to the notebook. Give me 1 second, because I have this pulled up. Well, actually, here let's just use this here. Okay, so I'm on figure 1, 2. If I scroll down, this is figure 29. And figure 29 is a continuous beam, 2 spans, uniformly distributed load. So this is the problem that we're after, okay, figure 29. Okay, let me go to the notebook real quick. All right, so here's the problem that we're doing. Now, just so everybody's clear, let's recognize, so this is the problem, and we're looking at, you know, I put it here down below. That's our analysis aid, okay? So we have that right here. In order to do this properly, I mean, look, these are all plug-and-chug equations, but there's an old acronym in engineering that garbage in equals garbage out. So that's just a way of saying that ultimately what matters is that you have the right inputs, okay? So in order to perform structural analysis like this, we need 4 values, okay? We need a W, we need an L, we need an E, and we need an I. Those are the 4 values that we need. Now, 3 of them are pretty easy because they're right there. W is the 1.5 kips per foot. E is the 4,000 KSI, and I is 2,500 inches to the fourth. Now, what I want to know is what's L? Is it 20 feet or is it 40 feet? Victoria says 20. I will tell you Victoria is exactly right. Look right here. Okay? Okay? Now look. That's the L value. Okay? Those images there, they matter because they reflect what's going on the beam. Okay? So that's L. Okay? Now, from there, it should be pretty straightforward. Okay? It should be a pretty straightforward expression. What I want to know is what's the maximum shear, what's the maximum moment, and what's the maximum deflection. And so we're going to do each of these. Okay? So let's start off with the shear. Now, if I look down here, now if you notice, there are three sort of point load expressions that are computed here. We have R1, these two reactions here, and then this shear at the bottom. Look at the shear diagram, okay? R1 and V1 and R3 and V3 are all the same. That's this magnitude. I mean, remember, what are your reactions? They're the first value on your shear diagram. So it would make sense that they're denoting it, that the reactions and the shears are sort of the same thing. That R2 is the jump on the shear diagram right here. Remember, that's how much you jump. But look at the plots and look at the magnitudes. Look at the diagram. V2 is the maximum magnitude shear on that shear diagram. That magnitude right there and that magnitude right there. Those are the maximum magnitudes of shear, and so that's the equation we're going to use. And in that, in that A, it says that V max, if you see that, is 5WL over 8. So what I'm going to say is V max is 5WL over 8. I'm not using WL squared over 8 or some old formula, or I'll go away, or something like that. I'm using the formula that is appropriate for the condition that I'm dealing with. Okay. And another thing that a lot of people are doing in class is they're saying, well, what if I have like a point load here? Let's say this is like 80 kips. Well, the whole beam is 40 foot long, so if it's 80 kips and it's 40 foot long, let's say it's 2 kips per foot. Don't do that. The worst case scenario is when that load is lumped in a particular spot. When you just turn the point load into a distributed load, you are violating statics. So don't do that. Okay, just go off of the condition that's present. And so this is 5 times 1.5 kips per foot times 20 feet divided by 8. Now I'm going to get Chad involved. What's the answer to that? There you go, 18.75 kips. That's exactly right. Now, somebody else in chat, where is that? I want to make sure everybody's clear on this. Where does the 18.75 kips occur along the span? Like, is that right here? Is that right here? Where is that? The middle, the central support. Exactly. All right. So that's V max. Now what about M max? Okay. M max. Now if we're looking at maximum magnitudes, just the biggest magnitude moment that we see, there are two moments that are listed. Okay. There's here, let me erase all this. There's an M1 and an M2. Now, here's the thing. If I look at this expression, okay, so let me circle this out. So I've got an M1 right here and an M2 right here. Okay, why doesn't it just list M max? Like if I look at those equations, just look at those formulas, which one's bigger, M1 or M2? Just tell me which one's bigger. WL squared over 8 or M1? M1, exactly right. M1's bigger. WL squared over 8 is going to be bigger than 9 WL squared over 128. So why doesn't it just list one value? Why does it list two? Okay, here's the reason why. Look at your moment diagram. M1 is the peak right here. Okay, that's that value right there. That's M1. Okay, M2 is this peak right here. So there's different peaks, or sorry, I got that backwards. This is M1, this is M2. Sorry, M2. So there's two different peaks on the moment diagram. M2 is in inside the spans, and M1 is right there at that middle support. Okay, so for the purposes of this problem, we're going to compute M1. But why both? Like, why would I, as a structural engineer, really care? Like, wouldn't I just use M1? Well, if we're talking about reinforced concrete design, the answer is no. I would need both. Okay, let's go back to a fundamental tenet of reinforced concrete design. Concrete is a material that behaves very, very well when it's subjected to compression. It behaves very, very poorly when it is subjected to tension. So concrete likes compression, it dislikes tension. So if I were to draw the beam, so here's the beam. This is just beside the point. So looking at your moment diagram, the beam experiences positive bending right here. It wants to smile. But right here along the pier, it's frowning, right? Because if you look at the pier, the beam is experiencing negative bending and it wants to bend like this. See, look below. Look at this image right here. That is what the beam looks like when it's deflected, right? Once it's deforming. So once it's deforming, it's experiencing zero deflection at the end and zero deflection at the middle, right? Well, across the pier in the middle, see how the beam is kind of frowning? See that frowny face right there? See how it's frowning? Well, why does that matter? Okay, the reason why that matters is that when a beam is smiling, we put the rebar in the bottom. When the beam is frowning, we put the rebar up top. So you would think the rebar pattern would look like this, but we actually do something a little bit different. So theoretically, that's where the rebar needs to stop, but that's not where we actually stop it. We actually take that rebar and extend it out a little bit further in each direction. I'm curious, does anybody in chat know how much further you think we extend it? Like if those green dashed lines are where we actually need to stop the rebar for based on the moment diagram, we extend it out a little bit further. How far, like what is this distance? How far out do we extend it? Like what is that extension out? Is that LD? That's exactly right. We extended out the development length. So those dimensions there are LD. That's exactly right. So we place the rebar where we need it to, based on the moment diagram, but then we have to embed it further into the beam LD. So think you're going to have sections of the beam that are singly reinforced and then sections of the beam that are doubly reinforced. Because if I cut a section through the beam like right there, I'm going to have rebar up top and on the bottom. So it's like a doubly reinforced section. So I'm going a little bit off on a tangent here, but I kind of want to come back to the concrete design and make sure that everybody's understanding what we're doing and why we're doing it. Now, again, for the purposes of this problem, I'm just going to chug out the M max and say that it is WL squared over 8. Now, it's not WL squared over 8 because that's the formula we always use and have been using the entire semester. It's WL squared over 8 because right there, that is the case. That is the maximum moment on this particular case. It just happens to be WL squared over 8. And so this is 1.5 kips per foot times 20 feet squared over 8. And so, sorry for shaking. What is that? 300. Wait, 300? I got 75. Did you do WL squared over 2? That right there is a perfect example. Do the calc and then do it again. You know, like do it completely fresh from scratch. And I guarantee it, like stuff like that you'll see, wait, I didn't get the same answer. Why didn't I? And you'll go back and you'll double check it. And again, going back to our discussion, this occurs at the central support. And then finally, we have our maximum deflection, which going back here, our maximum deflection, I'm looking at that box right there. The maximum deflection is WL to the 4th over 185 EI. And so that's the formula I'm going to use. And it says that that occurs about 4/10 of the span away from the support. So like if I look at my moment here, let me erase a lot of this. It's getting kind of cluttered. So I'm looking at this right here, and so if I come in this far, so if I look at my beam, that's about like right there. Like I don't know if you can see up here. I'm talking about right there, like not in the middle. It's not like half of L, like in the middle of that span. It's a little bit off to the side just because it's not linear. It's a curvy shape of the beam, so it doesn't quite occur in the middle. And so that is WL to the 4th over 185 EI. So that's 1.5 kips per foot times 20 foot to the 4th, 185, 4,000, and then 2,500 inches to the 4th. And then don't forget, we've got this deflection factor or conversion factor, 1728. And let me be clear, that 1728 is always used for deflections, period. You don't use like 1728 for distributed loads and 144 for point loads. The units always work out the same, so it's always 1728. All right. Somebody help me in chat. What's the answer here? Somebody who hasn't chimed in. There you go. 0.224 inches. And then for the heck of it, what I'm going to say is 0.4215 L is 0.4215 times 20 feet. And so when you chug that out, you get something like 8.43 feet. And so the reason I'm doing that is I'm going to say that occurs at 8.43 feet from the outer supports. Just so we know what is the maximum shear, what is the maximum moment, what is the maximum deflection, and where they occur on the beam. And the reason why I'm harping so much about the whole where they occur is because when you have multiple loads on the beam, you want to be able to add, your maximum shear from this case, your maximum shear from this case, maximum shear for this case, same thing with moment, same thing with deflection. Well, you can only add those up if they occur at the same spot, okay? So I want to make sure that everybody's clear that, if you have a given beam, that the maximum shear does occur in the same spot, or the maximum moment does occur, so that when you add them up, you know that you're good. If not, then if they don't occur at the same spot, then you kind of have to go a little bit beyond the design or the analysis age and just draw the shear diagram, draw the moment diagram, etc. All right. Does anybody have any questions about this? About this this calc, this problem, any of this? All right. I'm going to stop this share, and I'm going to share the homework. Okay. Now, I have here a different case in the for the homework assignment. Again, I want you to tell me what the maximum shear is, the maximum moment, the maximum deflection. I want you to tell me where they occur for this scenario. Now, I want to be crystal clear, okay? You have 0.8 kips per foot of a distributed load and then a 30 kip per foot live load, but that's concentrated. If you try and take that concentrated load and turn it into a W, turn it into a distributed load, that does not work, okay? It is not statically correct. Your deflections are not going to come out correct, and your moments aren't going to come out correct. What's going to happen is you're going to get less deflection on the beam, less moment on the beam than is actually present. If you turn that into a distributed load, you'll be under predicting the amount of moment and the amount of deflection. So you're going to have like two cases from supplement 1. I have table 3-23. I actually meant supplement 1. I'll update that on Blackboard. Table 3-23 is what we've been using in steel design. So you're going to have multiple cases from supplement 1. You're going to have one for the distributed load and one for the point load, and you're going to need to add those results up, okay? And so this homework is really just making sure that everybody's comfortable with how to compute the shears, how to compute the moments, how to compute the deflections, because the last thing that I want is for that to trip you up on the final. I don't want the structural analysis to be a problem at all. Any other quick questions before I sign off and go to steel? Like I said, I'll fix that to where it's not supposed to say table 3-23. It's supposed to say supplement 1. I'll fix that. I'll give everybody a minute to see if they have any questions. All right. Well, for those of you that are in steel design, I'll see you here in a few minutes. For those of you that aren't in steel design, what we're going to do on Friday is we're going to go to our final topic of the semester, which is arguably not, it's not just as easy as development length, but it's pretty easy, and that's columns, because columns are pretty straightforward in what we do in undergraduate concrete design. I think you're going to find it's pretty easy. That's all I got, everybody. I will see you all on Friday, except for those of you in steel. I'll see you here in a couple minutes. This is Squidward, I guess, signing off. We'll see you.